Hi everybody, welcome back. In this video I'm going to be going through a typical exam question of how to calculate Kc given some information that you using some information that you'll be given in an exam question. Now this is a really typical exam question, and it is quite straightforward once you have got yourself a system of how to work it out. So and I'm going to be using this reaction which is listed in your specification, so which just comes up time and time again. So we have, if we remind ourselves what Kc is the equilibrium constant, and it's the ratio of the concentration of the product to the concentration of the reactants at equilibrium. So what we mean is it's the concentration of those at equilibrium, not the initial concentration that you have when you start the reaction, the concentration that all of these are at equilibrium when the reaction has reached that point. So the reaction we're going to use is ethanol and ethanoic acid, an esterification reaction. So you're making the ester, ethyl ethanoate and water. So it's the reaction I gave you last time as well. So have a look at the information that's been given. So 0.1 moles of ethanol are reacting with 0.1 moles of ethanoic acid. The volume is 20 centimetres cubed, and then at equilibrium, once the reaction has reached equilibrium, we've now got 0.033 moles of ethanoic acid at equilibrium. Calculate Kc. Now, this is quite a simple example, but what I want to do is give you a foolproof method of how to work these questions out, so that if you are given a really complicated one in the exam, then you'll be able to do it, and you can just follow these steps if you get stuck, or to check yourself if you are happy with a different method. So I'm going to work through this one really slowly, and then I'm going to move on the next videos to slightly more complicated examples. So the way that I always work these out is using what's called a rice table. In other tutors and other teachers sometimes refer it to as an ice table, which is it's the same thing. I just use the R because in rice, because then I remember to write out the reaction. So if you write down the side rice, R-I-C-E. So R refers to the reaction. So write out your reaction, because quite often it will be on the top with a load of the question underneath. So if you write it out again, it will make it really clear. So we've got ethanol and ethanoic acid reacting to make ethyl ethanoate and water. Okay, I've tried to leave myself some space there, which is why I'm cramming it in there, but it shouldn't matter. Now you need to make sure the reaction's balanced, as is the case all the time. So make sure the reaction's balanced, because otherwise you're going to go completely wrong. And this reaction is balanced. So I, C and E, what they refer to is the number of moles of each of these different substances. So it doesn't refer to the concentration, it refers to the moles. So you can fill this table in using all the information from the question. So first of all, we are told that we've been given 0.1 moles of ethanol and 0.1 moles of ethanoic acid. And we've been told that they react, so that must be their concentration at their moles, number of moles at the start of the reaction. So fill that in, 0.1 and 0.1. Now, the other information we're given is the volume, so we don't need that right now. But at equilibrium, this is the next piece of information. So we've got, at equilibrium, there's 0.033 moles of ethanoic acid present. So we can fill this in here. Equilibrium moles, 0.033 moles. So what this means is some of the ethanoic acid has reacted, which we would expect. So that's all the information we've got in the question. The next bit of the table we have to fill in ourselves by just doing a little bit of thinking. So what can we fill in? We have here, with ethanoic acid, the initial number of moles, I keep saying concentration, that's wrong, the initial number of moles and the number of moles at equilibrium. So what the C stands for, again, is the change in moles after the reaction has reached equilibrium. So the change from the beginning of the reaction to the number of moles at equilibrium. So sorry, I should have filled this in already. At the start, so the initial moles is right at the start before the reaction started, we have 0 moles of the two products. We haven't got any, we haven't made any yet. So here, let's go back here. So at equilibrium we've got 0.033 moles. That means we've had a change of 0.067 moles. We can put a minus just to show it's decreased if you want to. But what's happened is we've started with 0.1 moles, decreased by 0.067 moles, and we have 0.033 moles left. Okay, happy with that? Now, the next thing we have to do is have a look at the stoichiometry of the reaction. So this is a really simple one to get you started. So we've got a 1-to-1 ratio of everything in the whole reaction, which is really handy if you ever get that. So what you have to think is that the number of moles where it says change, that's the number of moles that have reacted in the reaction, okay? So here we're lucky that the initial moles, we started with the same number of them, which makes it even easier. But it doesn't matter if we didn't start with the same number of them, because the key is the change will be linked to the stoichiometry of the reaction. So here we've got a 1-to-1 ratio, so that means the same number of moles are going to have reacted as the reaction has progressed. So we can say the change is 0.067. And because we started with the same number, 0.1, it means we're going to end with the same number at equilibrium, 0.033. Okay? So we've now got our number of moles at equilibrium of both of the reactants. Now if you have a look at the products, again we've got a 1-to-1 ratio, which is fantastic. So the number of moles that have reacted here is going to be the same, we're going to have the same change, the number of moles that's going to have been formed, except for it's going to be plus, so 0.067, and the same here, 0.067. So because we started with 0, this is going to be the number of moles that we have at equilibrium, okay? You don't need the plus. So hopefully that's really clear. Now you can work that, like I say, you can use this table to for any reaction that you're given, for any information, and I will give you some more complicated examples, but it is a really foolproof way of working out the number of moles at equilibrium. Now the next thing we have to do, although in this case we don't strictly have to do it, but I'm going to show you anyway, and then you can see why we don't have to. So that was just one of these little bits falling off. Is work out the concentration, because this is number of moles, and we need, for our Kc expression, and to work out the value of Kc, we need this information in concentration. So you should know from GCSE that concentration is equal to moles over volume in decimeters cubed. We've been given our volume in centimeters cubed, so we have to divide that by 1,000. So we do moles, whatever moles we've got, divided by 0.02 decimeters cubed. Okay? So I'm going to write out the expression, the Kc expression in full here, so you can see that I've done that. So Kc is equal to, we've got the concentration of the products first. So we've got 0.067 divided by 0.02 times by 0.067 divided by 0.02. I'm going to put it in brackets. I know that you don't need all of that, but it just makes it a bit easier to see. And then underneath we've got our reactants. So we've got 0.033 divided by 0.02 times by 0.033 divided by 0.02. Now you can put all those numbers into your calculator. What I would suggest you do whenever you do these kind of the calculations is to work out each individual bit and then plug it in, because if you try and put all these into your calculator, it's much easier to make errors when you type it in. So what I would recommend is either do each individual concentration or do the top line and then divide it. But hopefully you can see in this case that you wouldn't actually need to work out the concentration every time, because it cancels, because you've got exactly the same number of moles at the top as you do at the bottom of the expression. So you don't actually you don't need to do that in this case, but if you do, you still get to the same number, so it's fine. So if you prefer to work out the whole concentrations, great. If you prefer, you can cancel those out and just simply do 0.067 times 0.007 divided by those two. The answer you get is 4.1, I think. I've done it a couple of times. Hopefully, if you get a different number, check it. And you will need to work out units. Now, if you remember how we work out units, moles per decimeters cubed, moles per decimeters cubed, moles per decimeters cubed, moles per decimeters cubed. So they all cancel. So we have no units. So the KC in this example is 4.1, and that's it, that's the answer. Okay, so I'm going to turn this video off and make a new one with a slightly more complicated example. Okay, thanks.